All right, so now we are trying to finish up this last part, which is the reactions of the acids and bases, and then we will do the titration, which is very important. And there is going to be a question from titration on the test, final exam. And we are just going to be a brief introduction of buffers and then the calculations that relate to, buffer, calculating the pH. You're not doing that, because again, it involves the use of, calculators and log and all that. So forget about it. Okay, so here it is, the reactions of the acid. So this is the first thing, reactions of acids and bases. So first is reactions of acids and bases. So here we have when. First is when the acid, what happens when an acid reacts with metals. Acids reacts with metals. Now here, I would like to point out to something that is missing from your book, and that is the activity series. So here, keep this in mind that in between, I believe I can't write on it, but here, you have to make a note of it here. Between lead and copper in the activity series, this is just below this, what we covered initially, 11.3, strengths of relative acids and bases. Here is the activity series, okay, table 9.5, and that is on page 16. Between lead and copper, put hydrogen. So this means that all these species that are up, potassium, sodium, calcium, magnesium, aluminum, zinc, chromium, iron, nickel, tin, lead, all of them, when they react with acids, they're going to release hydrogen. But when copper, mercury, silver, platinum, and gold, when they react with the acids, first of all, they're never going to react with the acids. So they're not going to release hydrogen. So that's what I'm saying. Between lead and copper, above copper is hydrogen. So that you know that anything that is below hydrogen, no reaction with the acid. Anything that is above hydrogen, reaction with the acid to release hydrogen ion. So I'm going to just put here that the activity series 9.5. So refer to activity, activity series, refer to activity series, table 9.5, page 16 in handout. Okay, so what do you see here? You will see that let me write this down so I don't forget. So I have it with you guys here. Potassium, sodium, calcium, magnesium, aluminum. Potassium, sodium, forgot, potassium, sodium, and what was the other one? Calcium, magnesium, aluminum. Calcium, magnesium, aluminum, and after that is aluminum, then zinc, chromium, iron, nickel, tin, lead. Zinc, chromium, iron, nickel, zinc, chromium, iron, nickel, tin, and lead. And then all this is, then comes hydrogen. And then after that comes copper, mercury, platinum, copper, mercury, silver, platinum, and gold. Okay, so each one of these atoms will release hydrogen ion. So when they react, when these elements react with acids, they release hydrogen ions. or hydrogen gas, sorry, hydrogen as a gas. Okay, but these guys do not react with acids. That is why you make jewelry out of them. So here is this between lead and copper, you should put hydrogen. Okay, so now let's do these reactions. So now knowing that, so copper, mercury, platinum, gold, silver, platinum, and gold will not react with acids. The rest of them will. So now we have here magnesium as a solid. When it reacts with HCl as an aqueous solution, then this reaction is going to occur. So magnesium, actually, this is HCl is what? H is an acid, right? So magnesium actually reacts with chlorine and it displaces the hydrogen. So what does it form then? It forms, because magnesium is in group 2A, so MgCl2, okay, and it releases hydrogen as a gas. This is soluble in water, MgCl2, okay? So hydrogen gas, and then you balance it. So 2 hydrogens and 2 chlorines, 2 hydrogens and 2 chlorines, okay? This will happen. Next is look at the same story with zinc. Zinc as a solid, when it reacts with HNO3, that's a nitric acid. Then in that case, what happens? This is the HCl acid, hydrochloric acid, hydrochloric acid. This guy is the nitric, that's the name, nitric acid. Okay, so here what's happening? Here we see zinc is connected to the nitrogen, nitrate, and it breaks off this bond. So this bond just breaks. So it's just, you know, this is how these reactions work. So this bond is now with H2. So same thing. This is going to give you with, this is give you Zn NO3 whole twice, because zinc has +2 charge, nitrate is -1 charge. So that's the formula. Plus hydrogen ions, hydrogen as a gas. Okay, so this hydrogen gas is seen as bubbling. Okay, balancing. So that's what you have. All right, so 2 applies to the hydrogen, so that's why it's H2. 2 applies to the nitrates, that's why it's NO3 whole twice. Okay, so this guy is also soluble in water. So this is one reaction. Now, next is the reaction of acids with carbonates. In other words, the ones that contain CO3 and bicarbonates. Bicarbonates are CO3 -2. Bicarbonates are HCO3 1-. All right. Now, what do we have here? So we have here HCl as an acid, aqueous, reacting with sodium carbonate, Na2CO3. Okay, sodium carbonate is, you know, it's a sodium carbonate. Okay, anyway, so that is also soluble in water. So what does this give you? Hydrogen and chlorine. So sodium is going to combine with, remember, outer, inner, chlorine and sodium combined together, and this hydrogen combines with carbonate. Now, remember that even though it gives the carbonic acid, so let's write this down first, NaCl, okay, NaCl plus this gives you H2CO3, H2CO3. So this is 2 here, 2 here, and carbonate. So 2 sodiums, 2 chlorines, 2 hydrogens, okay? But keep this in mind that this is a carbonic acid, and carbonic acid is weak acid. So H2CO3 is a very weak acid, and this splits up, this breaks up. So it immediately, the moment it's formed, it gives you carbon dioxide and water. Okay, so it gives you H2O, and H2O is a liquid, and it gives you carbon dioxide, which is a gas. So all the bubbling is seen. Okay, so this is actually, this you can just look at it as the intermediate. Okay, so that's one thing with the carbonates. But if, let's say, HBr and NHCO3, for example, if you have HBr, hydrobromic acid aqueous, and this is reacting with NaHCO3. So let me write this name here. This one is sodium carbonate, and this one is sodium bicarbonate, the one that you use in cooking foods, baking. So sodium bicarbonate is also going to give you the same thing, same reactions. So here we have same story, NaBr, and this is also aqueous, this is also aqueous, and NaBr, and then this gives you water and carbon dioxide. So H2O plus CO2. So both of them basically give the same products. H2O, let me put this in a different color. H2O and CO2 is a common, ingredients. So here also H2O and CO2, common products. And then, NaBr. So the only thing when you balance it, this is Na, it's all balanced now. Okay, so this is just what you get. Okay. All right, so this is one thing. Next is the acids and the hydroxides. So that is the neutralization reaction. This is 1, this is 2, and then comes the 3, which is very important, and that is neutralization. Neutralization. Neutralization reaction is when an acid reacts with a base. So acid plus the base, in other words, hydrogen ion plus the OH ion. Okay, this gives you salt plus H2O, water. Okay, salt and water. So that water is that H2O. So now I'm going to just erase that, so it means that you can see it. Okay, now let's take some of these examples. Like, for example, the common one is NaCl. I'm sorry, not common one. HCl aqueous plus NaOH aqueous gives you NaCl aqueous plus H2O liquid. All right. That's the salt and water. So salt is not just NaCl. We can also have, like, for example, let's get another example here. H. So this is let's get another example. HNO, or let's do it this way. H2SO4 plus AlOH whole thrice. Okay, what is it giving you? This is still going to give you salt. So I'm going to just make another example because there's some space here. Let's look at this. HNO3 reacting with magnesium hydroxide, whole twice. Okay, so this is going to give you magnesium nitrate. This is also a salt, okay, and H2O. The rest is just balancing. So 2 hydrogens, and so there are 4 hydrogens. So you make them 4 hydrogens. Then you have 2 oxygens, and then you have 1 magnesium and 2 nitrates. Okay. So all of them are salts. So let's look at another one. So this is sodium chloride is a salt. Magnesium nitrate is a salt. Water is liquid. Magnesium hydroxide is a salt. Nitric acid is a salt. Now we are looking at this H2SO4 and aluminum hydroxide. So hydrogen combines with outer and inner. Remember? So, oh God, 1 second. Okay. So these two are going to connect to make water, and aluminum and sulfate are going to connect. So outer and inner. So we see that aluminum and sulfate, when they connect, then what is produced? And then we have this OH and hydrogen. So it's still going to be water. Okay, so now aluminum, remember, aluminum has +3 charge. Sulfate has -2 charge. So it is going to crisscross. So here we have 2 coming from the sulfate, and here we have 3 coming from aluminum, crisscross. If you have forgotten how to write the formulas, you need to go back and check it, and then the water is produced. Water, H2O. All right. So this is still a salt. This is still a salt. Okay. All right, now we have balancing. So we have 2 aluminums and 3 sulfates. So if we put 3 here, then 3 sulfates and 2 aluminums. And let's see. So there are six hydrogens on one side, and 6, 7, 8, 9 hydrogens. Let me write this down. Okay, so we have 6 hydrogens here, 3 sulfates here, okay, and we have 2 aluminums here, and we have, oh wait, so we have to just break this up, 3 oxygens and 3 hydrogens. Okay, now we have here 2 aluminums and sulfate. Let's keep the sulfate intact, SO4. There are 3 sulfates, there are 2 hydrogens, and there is 1 oxygen. Okay, so we see here that there are 6 and 7, 8, 9 hydrogens, 2 aluminums, 3 sulfates. So if you do this 3 twos are 6 and 3 sulfates. So sulfate and sulfate is balanced. Aluminums are 2, you put 2 here. So this becomes, sorry, this is not my mistake here. This is 2 times 3, 6 oxygens and 6 hydrogens. So this becomes 12, okay? So 12, oh, what am I doing here? 6 plus 6 H2O. Okay, so this is 6 times 2 and 6 times 2, 6 times 1. So that makes it 6 twos are 12 hydrogens. So 12 hydrogens, so 6 here and 6 here, so 12. So these are balanced hydrogens. Okay, so balanced hydrogens, and we have 3 sulfates, and we have 3 sulfates balanced. We have 2 aluminums and 2 aluminums, and we have 6 oxygens here, and we have made 6 oxygens here. Okay, so first balance. So here's a trick. Balance without putting the charges, without putting charges, because sometimes it becomes too cumbersome putting charges. Okay, so this is a molecular equation, balanced molecular equation. So I'm going to just write this again here, and then we are going to do the ionic. So molecular equation now is 3H2SO4 plus 2AlOH whole thrice. Okay, and this gives you Al2SO4 whole thrice plus 6H2O. All right. Okay. Now we have total ionic. Total ionic is 6. Now you put the charges. So there are 6 hydrogen ions. Oh, there's also aqueous. This is aqueous. This is aqueous. This guy is aqueous. This is liquid. It's important. Water is liquid. Do not ionize water. So hydrogen ions are aqueous, 6 of them. 3 sulfate ions, aqueous, put the charge, -2, this is -1. There are 2 aluminums, charges +3, aqueous. Okay, so aluminum is in group 3A, so +3 charge. And moreover, crisscross, you see it is combining with 3 hydroxide ions, so it's +3 charge. Hydroxide ions are, so let's just break this up. There are 6 oxygens, and the oxygen will have a -2 charge. And there are 6 hydrogens. Hydrogens have a +1 charge. And this whole thing is the OH, 1 negative, aqueous. So just split it up like that, okay? This gives you 2 aluminums +3 charge aqueous. And this is the sulfate ions, 3 of them, -2 charge aqueous, okay, plus H2O. So there are 6 H2Os, and we are not going to do not ionize water. Okay, so now look at hydrogen ions, 6 here, and 6 hydrogen ions here, and they are in the aqueous. This is aqueous, this is aqueous. Okay, so aqueous are giving you 6 + 6, 12. So there are 12 hydrogen ions here, hydrogens here. Okay, but change of state is seen. Same story with the oxygens also. You have 6 oxygens here, and you have 6 oxygens also here. So that's also showing the change of state, which is coming from basically this OH. Okay. Next is, look at this. 2 aluminums are aqueous on the reactant side, and 2 aluminums are aqueous on the product side, spectator ion. 3 sulfates aqueous on the reactant side, and 3 sulfates aqueous on the product side. Okay, so what do we see here now? That spectator ions are which ones? Spectator ions are 3. No, let's put this here. 2 aluminums +3 charge aqueous, and 3 sulfates -2 charge aqueous. Okay. All right. Then comes the net ionic. Net ionic is hydrogen ion going from, and there are 6 of them, 6 hydrogen ions. No, sorry, actually there are 12 hydrogen ions. 12 hydrogen ions going from the aqueous medium, combining with 6 oxygen ions minus 2 aqueous medium, right? Or you can also look at it as 6 hydrogen ions, aqueous medium, combining with 6 OH ions. These are actually 6 OH ions, aqueous medium. That's better. You know, that's better to put it that way. That's better because it's the OH. It's actually the final reaction is with the OH only. So put it this way. So hydrogen ion, 6 of them, aqueous, plus 6 OH ions, aqueous, gives you 6 H2O. Okay, liquid. Okay, so spectator ions are the ones that do not show change in state. And the net ionic is all those ions that show change in state. So you've seen that going from the aqueous medium to a liquid. Okay, but the other ones were not showing any change of state. 2 aluminum aqueous and 3 sulfates aqueous on both the sides. Okay, so this is your ionic and the net ionic equations. So net ionic equation is always going to be between water and, you know, OH and hydrogen and OH ion, always. Okay, so the same thing, you're going to show, write a balanced equation for the reaction between sulfuric acid and potassium carbonate. So just remember that anytime there's the carbonates or bicarbonates, water and carbon dioxide is produced. Now comes the last and the final, and that is the titration. Very important, titration. And I'm going to just let you know that this is going to be on the test. All right. So now we are looking at the titration. Okay. Here's the thing. Let's do this here. You are given what is the molarity of HCl NaOH? Okay. Okay, so here is the situation. You have HCl, which is aqueous. That is a very clear, transparent solution. Simple. All right, clear. Reacting with NaOH, and that is also aqueous. And that is also a very clear, transparent solution. When they mix together, they produce salt. In this case, it's NaCl, which is also soluble in water. And so once that salt becomes soluble in water, remember, it gets solubilized or hydrated. And so what do you see? This is also forming a clear solution. And there is water, which is a liquid, but that also is a clear liquid. So here is a problem. How do we know that the actual reaction has occurred? If all of them are going to be clear, there's no way for us to know that final product is formed, or all of the HCl has been used up, or all of the NaOH has been used up. Okay, so in order to, let me write this down, in order to determine whether all of HCl or NaOH has been used, we need to use an indicator. So what does the indicator do? Indicator tells us, when all of HCl or NaOH has been used. Okay. By showing a color change. Okay. And that color change indicates the endpoint. Endpoint. What is endpoint? Endpoint is when the reaction is complete. Okay, simple. Now, phenolphthalein, phenol PHTHALELIEN. Okay, I don't know what the spelling was. Let me see if it is LIEN or LEIN. EIN, phenolphthalein, yeah, okay. So TFNOLPHTH, oh, phenol, PHTHALEIN gives pink color with excess OH ions. Okay. So whenever there are the basic solutions, whenever there are bases, phenolphthalein is pink color. Phenolphthalein is colorless with the acids. Okay. Colorless with acids. No color. Okay. So when all of the hydrogen ions are used up and no more hydrogen ions are left, then the only thing that is left in the solution is the base. Then we would see the pink color forming. So let me write this down. When all of the hydrogen ions are neutralized by the base and no more hydrogen, or there's only excess base left and no more hydrogen ions are left, only slight excess of OH ions from the base, then we see pink color. Pink color. Okay. Light pink indicates end of the reaction, end point, end of reaction. That's the end point. When all of the OH ions, no more OH ions, no more hydrogen ions left, no more hydrogen ions are left. Okay. No more hydrogen ions are left, and only, little bit slight excess of the hydrogen ions. So that's just a little bit, light pink color is what you need. Okay, so this is the basic, setup or the theory behind this whole titration. Now, how do you set up the apparatus? So here's the thing. We take an apparatus which is called burette. Okay, so this is the, actually, I have to, okay, let's do it here. Okay, here is the burette. Like that, it looks like that. It has got markings on the top, and mostly it starts from 0 and all the way goes to like 50 or so forth. Okay, milliliters. So your reading is going to be in milliliters. Here you're going to put an Erlenmeyer flask, and that Erlenmeyer flask will have some amount of acid. So through a pipette, this is what you do. You are going to add the base here, fill up the base. So base is here, and this base is filled up. And there is some acid here, slight acid, and I'm going to just leave it, some color, or actually I don't want to put any color. Right here is the acid. Oh. Okay, not even that, sorry, some amount of acid. So let's say 25, how much is it? What is the molarity of the HCl solution? It's 28.6 milliliters. Or let's do this here, 28.6 milliliters. Let us say 28.6 milliliters of HCl. $25, sorry, my mistake here. Okay, this is 25.0 milliliters of HCl is put here first. We need to find the molarity of HCl. Find the molarity of HCl. So this is used, titration is used to find the unknown molarities. So molarities of like the acids, or generally, the acids. So we need to find the molarity of the acid. So used a technique that is used to find the molarity of unknown. It could be acid or a base, but generally it's the acids we use. Okay, so this is your unknown. This is unknown. Okay. Actually, 1 minute, because this is taking too much of the space here. I will just make this small so we have sufficient space to work with. Okay, so this is right here. Okay, now better. Now this guy, we need to move up, so there's plenty of room to work with. And it's not at the base. Okay. All right, now let's look at this. So the molarity of the acid is unknown. We need to find that. Here on the top, we put the base. So the base molarity is known. Molarity is known. Molarity of the base is known always. Or like not always, like one of the molarities will be known, but mostly it is the base here. So we are using NaOH, and we found that. Now, before even we move further, what we are going to add here is, you are going to add into this, add the indicator phenol, T-H-E-L-E-I-N, phenolphthalein indicator. Okay, this phenolphthalein indicator is colorless with acids, colorless with acids. Okay, so you've added the phenolphthalein indicator and you've added 25 milliliters of HCl in the, this is called the Erlenmeyer flask. ERLENMEYER flask. Okay, and then you use a pipette to put that because pipette gives you the exact, but okay, but here is the burette. This is the big one, and then again it's clamped and everything, so I have a video of this, so that when you add the base here, you're going to use a funnel. So I highly recommend that you watch that video. Okay, so now once you put the base here, you have it, this whole setup. Now you open the burette and you start dropping the base into the acid. As the acid and the base meet, hydrogen and the OH ions react. OH ions are going to neutralize the hydrogen ions. And we initially will not see any change in color. But a time comes, slowly, we notice that the color begins to change to pink color. So the lighter pink of it, and then it evaporates, and then it just vanishes, and then it comes again, and then it vanishes. But a time comes when it stays, when the pink color stays, when the pink color, let me write this in pink only, when the pink color stays, pink color stays, then reaction ends. That means all the hydrogen ions have been neutralized by the OH ions to give you water, and there is only a little bit extra OH ions. That is why they're giving you the pink color. Okay, so in this case, we see that we were given the molarity of the HCl given is 0. Molarity is 0.175 m. And when you dropped it, a time comes when the color persists, when it stays. So all that, from the top till here, the amount of base has been added into the acid, and that is equal to the volume is 28.6 milliliters. Okay, so now the question is, so this is also study check. Study check 11.12, and you see here that you are given the HCl, you are given NaOH, you are forming NaCl and water, and fine, all the reaction is done and fine, but we need to find the molarity of HCl when the volume of HCl was 25. So let's just put this A for stands for acid. This is acid. So 28, this is 25.0 milliliters. And then NaOH, the molarity of the base and the volume of the base. The molarity of the base is 0.175 m. And the volume used is 28.6 milliliters. So what is the process here? How do you find the molarity? This is what you need to find, the molarity of HCl. Okay, so what is the steps? So first of all, always convert the milliliters to liters. How? You are going to use 1 liter over 1000 milliliters, and that gives you this liters. Second thing is find the moles, find the moles of base. Find the moles of the base. Okay, that is, how do you find? The formula that you're going to use is moles of the base is equal to the molarity of the base times the volume in liters of the base. That gives you the moles of the base. Next is you're going to write here, then using mole to mole ratio from balanced equation, using mole to mole ratio from balanced equation, find the moles of acid. Okay, so we have the moles of base times whatever the mole to mole, the acid from the equation and the base from the equation, you know, and whatever the coefficient is, you know, whatever this number is from the reactions and whatever this number is, and that's going to give you the, sorry, this is the moles of acid. Now by this time this has become the moles of acid. And wait 1 second, no, this is the moles of base. Yeah, moles of base, and this is going to give you the moles of acid. Okay, next is you are take the moles of acid, divide by the volume in liters of the acid, and that's going to give you the molarity of the acid. Okay, so let's do this now. So first is 28.6 and 25. So let's do this first of all. First, 28.6 milliliters times 1 liter over 1000 milliliters, and that is 0.0286 liters. Okay. The other one is 25.0 milliliters times 1 liter over 1000 milliliters, and that is 0.0250 liters. That's the first step. Second, next is you are given 0.175 molar. So the moles of base, moles of the base, here you have NaOH, is equal to molarity of NaOH times the volume given in liters, volume in liters of NaOH. Okay, so you have now the moles of NaOH. Moles of NaOH is the molarity is 0.175 m times the volume is 0.0286 liters. So you get the moles of NaOH is equal to so we just do the calculations here. Give me 1 minute. Okay, so 0.175 times 0.0286, and that is equal to, excuse me, 0.0050 0.0050 0.05, so we can just leave it like that. So these are the moles of NaOH. And next is the moles of HCl. So the moles of HCl are coming from the mole to mole ratio, mole ratio from the balanced equation. Now here we see it is 1:1, okay, 1:1 ratio from the balanced equation, but it can change, it depends. So from the exams, you know, just make sure that you do the balanced equation, okay? Okay, so now we have 0.0050 moles of NaOH, okay, times 1. So from the balanced equation, as you can see from the balanced equation, it's 1:1 ratio. Okay, and fine, this is also given 1 mole of NaCl and 1 mole of water, but it's 1 mole of HCl and 1 mole of NaOH, 1:1, same moles. So 1 mole of HCl from the balanced equation and 1 mole of NaOH from the balanced equation. Okay, so this gives you, that is equal to 0.0050 moles of HCl. Okay, so these are the moles of acid. Okay, now we have the moles of acid, we have the volume of acid, you can find the molarity. Molarity is equal to moles over the volume in liters. Let's put this here, volume in liters, always liters. Okay, so the molarity of HCl is equal to the moles of HCl over the volume of HCl. Okay, volume of HCl, and that's in liters. So let's put this here, M is equal to 0.0050 0.0050 moles over 0.025 liters. Okay, let's do this. So 0.0050 divided by 0.025, and that gives you 0.20002. So just, you know, just 0.200, or you basically, you know, if you look at the significant figures, 2 significant figures here too, so it suffices to just keep it at 2. So 0.020 M. Okay, that is the molarity of HCl. Always write down in what context these calculations are. Molarity of HCl. All right. So this finishes the titration, and there is going to be a question from that. And now last but not the least is the buffers. Now buffers, just so for your knowledge, you know, this one was what, 3 and then 4. 4 is the buffers. Okay, buffers is when the pH is maintained. That is a buffers scenario for solutions. Okay, so whenever the pH is maintained, whatever the original pH of a substance is, and when that is maintained, that is buffer. So for example, here you have, let us say, this is an example of a reaction. You have acetic acid, which is a vinegar, acetic acid, okay, so CH3COOH. This is the actual formula. When it reacts with water, it gives you acetate anion and the hydronium ion. So when it reacts with water, it gives you, and again, equilibrium all the time, it gives you the hydronium ion, and the acetate anion. Okay, so let's write this down. Acetic acid is CH3COOH plus H2O in the aqueous medium. Aqueous, this is liquid, and this gives you the give me 1 minute. Okay, this gives you the hydronium ion is H3O plus aqueous, and the acetate anion is CH3COO1 negative, and that's aqueous. All right. So here's the thing. It's in a scenario where, remember that this is an acid, acetic acid, reacting with water, which is acting as a base, and the acid gives, this is the conjugate base of CH3COOH. And I don't know what's going on here. Oh, just a minute, guys. Sorry, fireworks. Okay, fireworks happening outside. Anyway, so this is the conjugate base. Then hydronium ion is the conjugate acid of water, H2O. Okay. Okay, so now let's look at this. So we have the acetic acid. When it reacts with water, it gives you hydronium ion and the acetate anion. Acetic acid is a weak acid, but it has a strong conjugate base. Water is a base, and the hydronium ion is a conjugate acid. So conjugate acid, so water is a weak base, and the conjugate acid of water is the hydronium ion, which is a strong acid. Okay. Now, what happens is it's basically a relationship between an acid and a conjugate acid. Oh, sorry, an acid with a conjugate base. So here we see the acid is the acetic acid, and its conjugate base is the acetate anion. So acetate anion, basically, okay, there's something that we did not study in this chapter was the salts. So that's something which we needed to study. That's why I was not comfortable, like, you know, going into much details about the buffers. But anyway, so think about it. Sodium acetate, that is a salt of acetic acid. So sodium acetate is the conjugate, so it leaves the sodium aside, but the acetate anion is the conjugate base of acetic acid. So I'm showing it as Cb. And it is the amount or the concentration of the acid and its conjugate base which, you know, which balances out the pH, which keeps the pH stable. It doesn't make much of the change. So that is why if you have an acid, and if you want to maintain the pH of that acid for a long time, then you need to add, you know, make it a buffer. So you need to add the conjugate base of that acid, and the conjugate base of that acid, like generally it is in the form of salts, like sodium salts and so forth. So now we have here the acetic acid and the acetate anion. Acetic acid is releasing the acetate anion anyways, but more of the acetate anions have been added, can be added, you know, from sodium acetate and so forth. Now, in case in this solution, if you increase the base, increase the base, you add some more base, like so, like bases like the OH ions, you know, you add sodium hydroxide. Okay, what is going to happen in the sodium hydroxide? Remember, it's the OH ions are going to then combine with the sodium. sodium hydroxide. And then sodium is not available to combine with the acetate anions. So that is why we would see that the concentration of the base is going to increase. Or in other words, we would see the conjugate base increasing. So here, when you add the OH ions, it's only slight increase happens. And we would not see this. So a little bit excess of the base increases if you add sodium hydroxide, because remember, then sodium is not available to combine with the sodium acetate to make sodium acetate. The acetate ions are now removing free. More amount of acetate ions are going to be available. That's what it means. Now, if you bring an acid, then what happens? Now, all that excess acid that you had, now that acid is obviously going to now increase the amount of acid. So more hydronium ions are coming already. What was I saying? The ions, like the more acid means that the concentration of the hydronium ions is going to increase. That's what it means. And then the concentration of the base, the conjugate base, that is the acetate ions, doesn't change, but the amount of the hydronium ions increase, the hydrogen ions. Okay, so that's basically what it means. Okay, so, you know, this is just to give you a brief idea of the bases, the buffers. But I'm not going to ask you any questions on that. Just to keep this in mind that in buffers, the pH is maintained. Sorry, buffers, the pH. Oh, I'm so sorry. Just pH is maintained. Okay, so that finishes this chapter, and in a way this finishes your course as well. And now we only have one last chapter, which is the one on nuclear chemistry, and that is just a video based, you know, just lectures on the videos, and very interesting videos, and I have uploaded several of those videos. You guys should watch them, and I'm going to explain to you, you know, next week or week after next. But next week is a happy Thanksgiving. And so I've finished this chapter already, so we're done, right? So you have everything now, and hope it helps you to prepare for the test. You have 1 week to go, but in case you don't understand something, you can always check with me on Monday or on Tuesday, you know, whenever your whenever you have your office hours, or you can just send me an email. Okay, guys? And so I look forward, if you have any questions on your grades, you can also check with me, but grading is a progress. I'm behind on the grades a little bit because just so much work with online grading, and the internet has been really going very slow. So it was hard for me, but I will catch up, and I'll be giving you feedback. So please read it. And if you have any questions on that, don't hesitate to ask me anything. Okay, guys? All right. Thank you, and happy Thanksgiving, and enjoy studying also for the final exam, and also for your preparation for the presentations, and also for test 4. Okay. Thank you. Take care. Bye-bye.